Wait ka sa
Miss, excuse me, Miss. Naka-mute imo nga microphone, Miss.
Okay. So what I have written here, class, is the transfer function of a first order system. This is your input, the Laplace transform of your input in deviation form, and this is the Laplace transform of your output in deviation form. So I hope you have fully understood that you cannot get the Laplace transforms of your variables in your particular model differential equation if your variables are not in deviation form. So if you may be asking what are these deviation form of your variables, it's your particular variable at any particular time representation minus its representation at the steady state. So that's your deviation variable. Once it's already in deviation variable form, then you are ready to take the Laplace transform of that particular variable. So in this case, when you derive the the transfer function of a first order system, this is your corresponding form. And for all first order systems that we're going to tackle, class, this will be its transfer function. You have 1 as the steady state gain because the numerator is always at all times 1, except for one particular system. You'll know that system later. And the denominator, it's always the denominator, class, that is uniform. So for all first order systems, the denominator is always for the transfer function tau s plus 1. The tau here is the time constant, and it's a characteristic of a first order uh, transfer function. It's always there multiplied to the s in the denominator. Now I will start with the simple forcing function and that of the unit step function. So your unit step function is represented like this. And in terms of a disturbance, it's a sudden and sustained disturbance. Sudden and sustained type of disturbance in your system. So what probably an example for that is a change in the concentration of one of the feed at stock to your reactor. If that particular change in concentration was not changed after a very long time, then it's a sudden and sustained type of disturbance. This is the representation of the forcing function for a step input. Now, its Laplace transform is 1 over s. Okay? So in deriving the response for this type of forcing function, what was done in your textbook actually is solve for y of s with x of s being this one already. So you have 1 over s times tau s plus 1. How do you get the y of t here? You just simply invert this expression using methods of partial fraction or the uh, what do you mean this? By the corollary of the Laplace transform of the integral, because you have here this expression 1 over s. For it to be easier, for it to be easily handled, when you do inversion of Laplace, you may divide both the numerator and the denominator by the tau. So now your numerator will have 1 over tau. And your denominator will be s times s plus 1 over tau. Now, you have already two linear factors here, and you are ready. By the way, class, this is still y of s. We have not yet inverted, so it's still y of s. And to get the y of t for this y of s, which is now the response, it's now the response to this forcing function. This is your forcing function, and this is the response. All you have to do, so you have 1 over tau there, you need to invert 1 over s times the quantity s plus 1 over tau. I think you know this fully well because you encountered this in integral calculus down to DE and down to Laplace transformation then. When you had your advanced engineering mathematics. So the corresponding response, can anybody here tell me what's the response for a step forcing function based on what you have read and listened to? What's the response to the step forcing function? Because the one that I use here as an example is a step forcing function or a unit step forcing function to be exact. If this has a magnitude of 10, then we refer to it as a step forcing function of magnitude 10. And all of this will also have a 10, this will be 10, this will be 10. So you will just simply be having the same expression to invert. Now, what is the response to this particular type of input, the step input? Okay, let me check on the chat box if somebody wrote something. Oh, nobody wrote something. So what is the response to this particular forcing function, the unit step forcing function, based on what you have listened to and what you have read?
10 over S, Miss.
No, what I'm asking is, sorry, what I'm asking is, I can see the, wait class, I can see, where is it? Wait, I'll stop sharing, I'll share again. I can see the next page arrow. Oh my, I erased everything. Wait class. What happened? Anyway, so I write again. I don't know why everything was gone. If your forcing function is x of t equal to u of t, what is your response? So this is your response. This is your input. This is your output. So that's what I'm asking about. So I said a while ago that the response to this particular forcing function is 1 over tau inverse Laplace of 1 over s times the quantity s plus 1 over tau. That's what I mentioned a while ago when I got cut. So I'm asking you, what is the answer to this inverted rational expression in s that will now represent the response to this particular step or unit step forcing function? Okay, let me check. Somebody wrote in the chat box. So if I get rid of the 10, so that would be 1 minus e raised to negative t over tau. So that would be 1 minus e raised to negative t over tau. Now, let me present to you again the slide. That way you will know what I'm trying to emphasize here. Which of the words here belong to transportation? And there's another one. There are three. Bicycle, airplane, and what's the other one? President is the president of transportation. Okay, so I'm here now. I'll share the slide to you. So based on what you have listened to yesterday, This is the, let me annotate, this is the response to a step forcing function of magnitude A. So if it's a unit step function, for those who have answered in the chat box, that is correct. The response to your forcing function is 1 minus e raised to negative t over tau. If I may say, your response to a particular step forcing function is dependent on two things. It's dependent on the time duration in which that particular response is to be measured, and the tau, which is a characteristic of the system. Of course, it will be dependent on the magnitude, depending on what is the magnitude of your step forcing function. But generally, in terms of the formula, since A is a constant and it's stated in the problem, unless otherwise that you're the one asked to determine this first, your response will be dependent on the duration or the time in which the response is to be measured and the tau of your system. Now, if it's plotted class, this is the response curve that will be produced. At 0, the slope of this particular response curve is 1 over t. Now, it's explained further in your text if you have read the explanation as to the percentages in which your particular response reaches the steady state value. In the case of the forcing function, you have it only until at time 5 tau, you could say this 5t, your forcing function reaches around 99.3% of its ultimate response, or that is its steady state response. At time equal to tau, by the way, this t's class are tau, the t here is equal to tau, that at the time equal to tau, you could see in the graph that your forcing function reaches 63.2% of its ultimate value. The ultimate value that we are referring to, class, is by the time in which this curve here flattens. So this is the ultimate value. Why? Because we don't see any change anymore. But ultimately, speaking of the ultimate value and looking at the response curve, or the plotted response for our step function of magnitude A in this case, what is the ultimate value, if I may ask? Or in other way of stating it, what is your y of infinity? That's your ultimate value. So what is your ultimate value for the response in this case, looking at the graph? Thank you, Earl. Very good. So your ultimate value is 1. Now, if you can't quite see it clearly here, the part of the graph where this particular curve is straightened out, no variation anymore as to its slope, it's actually 1. But mathematically, if you go back to your response equation, if this is just simply 1 here for the magnitude, if you substitute t equal to infinity here, e raised to negative infinity will be 0. So that tells you that the ultimate value of the response is 1. Meaning after a very long time, the ultimate value of your response is 1. If the magnitude of the step input is, let's say, 25, its ultimate value after a very long time is also 25. So we say, if we're talking about the A that we're talking here, then the ultimate value of the response is A. Okay, now when you encounter problems concerning sudden and sustained types of disturbances, the key points that you have to recall is the A. So you have to recall what is the A, then you need to determine the T, and then you have to determine the tau. Oftentimes, the tau is stated in the problem. The time elapsed is also stated. That way you'll be able to determine the corresponding response. This particular A class sometimes is not spelled out in the problem na hambagin na the magnitude of the step change is like this. You are the one who's going to determine it. How will you determine it? So if I will ask anybody here, how will you determine the A? Because there are problems which does not specify the magnitude of the step input. And you can read this actually in the sample problem also that is given in the part in which you are to read. Okay, somebody wrote on the chat box. Okay, somebody in the chat box wrote. So my question is, how will you determine the A if the problem does not specify its value? Seldom, or in most cases, class problems on step input does not give you specifically the magnitude of the step change. How will you determine the A? Okay, the value of the A here, when you determine its ultimate value or its value after a very long time, another way of stating it in some problems, its steady state value is actually determined using the final value theorem. That is correct, Aliana. But what I'm trying to ask is, if you are not asked for the final value of the function or the ultimate value of the response of your forcing function, how will you determine the magnitude of the change in the step input? So I'm asking, how will you determine the value or the magnitude of the change in the step input, not the output? How will you determine the A? Difference of the final and the initial condition. Decrease or increase in the temperature, find the difference. Very good. Okay, so having said this, I will just clarify, so I will clear my markings here. What I'm trying to ask from you a while ago is this: the A, the magnitude of the step change in your forcing function. This same A is actually the A that appears here. How do you determine this? You determine this based on the difference. So you have mentioned about temperature difference. So if we go back to the thermometer as the physical system that was used also in the discussion in your textbook, this A is actually your X minus XS. Now you may ask me, what is that X and XS? Or specifically, I write here X of T minus X of S. In conditions wherein, for example, in the case of the thermometer, your thermometer initially is mentioned as at a steady state reading of, or has a reading of at the steady state condition. That particular initial reading, you're right, is X of S. That's your X of S. Sorry, class. That's your X of S. And if that particular temperature thermometer, which has reached steady state value, was placed in an environment other than the one, or having a temperature other than the one which is being registered by your thermometer, that would be the new read, the new temperature of the environment. So from one environment, let's say in a room at 25 degrees Celsius, that's your X of S, because it's understood that your thermometer is equilibrated at that particular temperature of that environment. Now, if that thermometer was transferred to, let's say, a glass of water, a glass of boiling water, if of course you're going to place it there, your X of T will be the temperature of that boiling water, let's say 100 degrees Celsius. So let's say initially your thermometer registers the room temperature. So correspondingly, your A, the magnitude of the step change is 75. You get the difference of the new environment where your thermometer is placed into with the steady state reading of that particular thermometer. So that is in the case of the thermometer. If it's another system that we're talking about, it would simply be the steady state value of the input, whatever is the input may be, minus its current value where the change has been recorded or observed. So kung ano siya ang current value, kung ano ang steady state value, isubtract lang na ang duha, that will be now the magnitude of the step change. If it's in the case of the step input. Okay? Now, before I go to the next type of disturbance, Do you have any question regarding the step input? So it's clear. You need to know the A, you need to know the time elapsed, and you need to know the tau. So there may be a question here. Miss, do we need to really start writing the x of t, then x of s, then determine the y of t from the resulting y of s? The answer is no. Once you already, or since we have already derived all the response equations, you need not go back to the basics of having to derive those response equations. I'm only interested if whether you are able to supply or apply the appropriate values to your response equations already. So no need to derive this particular response equations. Okay, so diretso na kamo mag-solution kamo, sulat lang ang given, required, and then sa solution nga part, no derivation should be needed anymore. Okay, directly substitute. Directly substitute the values that you can pick out from the problem. Okay? Okay, Joshua, you're raising your hand.
Hello, Doc. Good morning.
Morning.
Na-curious na ko, Doc. Nga sa zero, nasa ma-start per me, Doc.
Kay sa actual processes, Joshua, the time in which a particular disturbance occurs, it's always time equal to 0. Like for a particular system at steady state, it's at steady state. Once there's a particular process variable that changed already, resulting to, of course, a change in the value of the variable that we're trying to control or monitor, that time in which that change occurs is time always equal to 0. So 0 onwards, that's the time elapsed for such particular disturbance effect on the response of the system to be measured. So we always start equal to 0. Kaya sa actual processes, wala man ta negative time. Ang atong time always positive na. So we start with 0 onwards. So that is why you see here, response for t equal greater than 0. At the time that disturbance started, that's time equal to 0. More questions? Okay, there's none. So I will skip this one. I think everybody is already, I think more or less you have 80 to 90% understanding of this. If you don't have any more questions, then we go to the, okay, let me just clear the ones. Okay, the next type of forcing function, I'll just use this one, I'll not discuss it the way, it's the ramp. So it says here that the ramp is a steady increase, a steady, it's not always increase, but most of the time plus it's increase, but it could be also a steady decrease in the value of the input. So in industrial processes, it's a drifting type of disturbance. Changes that are either increasing or decreasing for some period of time. But that decrease or increase is a constant, just like a line here. For the slope of this line, it's a constant. So the rate of change is approximately constant. Now, in Kauhanor, I will write it here. Your forcing function for this type of disturbance is AT U of t. It's always U of t, denoting that the disturbance started at time equal to 0. Because our unit step function has a value of 1 at time equal to 0 onwards. It's t equal or greater than 0. So that is why it's always affixed to the representation of the forcing functions. So this is your forcing function equation for the ramp input. Now, if you take its Laplace transform, you need to go back to the basics. That would be A over S squared. Why do we have this? Because we took the Laplace transform of the t, which is 1 over S squared. If you're interested with the y of t in this case, it's the same thing. You have to go back to the transfer function, which is 1 over tau over s plus 1 over tau. You have that. And then your corresponding y of s would be now this x of s, this one, your a over tau, then I'd like to write here. Okay, I have grade 2 students here. Oh, 1 over tau. The expression that you need to invert will now constitute the product of x of s, which is a over s squared. The s squared is in here, the a is in here, and this one, the 1 over tau over s plus 1 over tau. The tau I already placed in here. When you have this inverted, which is just the same, the procedure is just the same as that for the step input, that's method of partial fractions. I'd like to clear here the markings. Your your response will be this entire equation. So this is your entire response. Okay, all the b's here that you see the letter b in Kauhanor, it's equivalent to capital letter A, because the magnitude of the change of the disturbance in Kauhanor in our book is always represented as capital letter A. So in this case, I placed here a B because we started with a representation. Let me go back of B here. The magnitude of the ramp change. The magnitude of the ramp change in the input is represented as B. So that is why you see also B in here. So this is your response equation for the ramp forcing function. This is the response to a ramp forcing function. In here, you need the magnitude of the ramp input, whatever is that A. You need the time, of course, when you want to determine the response already. So the problem makes this known. It would ask you for what would be the response after 10 seconds, or what would be the response after 1 minute. So that's the time that you're going to place in here. The tau is a characteristic of the system, and the problem will also make known of that. And you have this. So what I'm trying to tell here is that if you invert the expression I wrote a while ago, this will be the corresponding answer to that particular rational expression in S. Now you could see, okay, di ko mag-discuss, dali. So I would like to ask from you. You could see that there is B tau in here, product of B tau. Can anybody tell me what does this represent, or what does this particular value imply? Or what's your understanding of this B tau? You can write on the chat box if you want. What is this particular value of the B and the tau? The B, remember, is the magnitude of the ramp change, and the tau is your time constant. So what is that? Actually, my question is there already. Oh. The answer to my question. Difference in input and output. Aliana wrote, it's the difference between the input and the output. Okay, do you have other, do you want to polish what Aliana wrote there? You want to add something, or is it already like that? The product of the B and the tau. Okay, Aliana is correct, but it has to be as we need to polish it. You see this one, it's written here. It's written here. It's the steady state difference. Whenever you see terms, phrase like steady state difference in a particular problem class or statement, it means after a very long time. Because if your system has deviated from its steady state value due to an external disturbance, after a very long time, it will reach a new steady state value. So after a very long time, if the problem will ask you for a particular response to a ramp input, after a very long time, what is the difference between the response and the input, whatever that particular physical system is? After a very long time, that would simply class require you to multiply the magnitude of that ramp input with its time constant. Meaning, sa kadugayon, ang difference ng imo output, sang steady state output mo, kag sang imo input before natabo ang external disturbance is the product of B and tau. Steady state difference, again, represents the ultimate steady state value after the disturbance occurs. So that should be your answer, a simple product of B and the tau. Okay? Now, I'll go to this. It's represented here. Output lags input by tau. Now, in practically all forcing functions class, the output always lags behind the input. The output only occurs, or the response only occurs, because of the changes in the input. So in this case, in the case of the ramp input, your output will always lag behind it by tau. Now, for it to be understood clearly, miski mag-Ilonggo, okay lang sa akon, what is your understanding of this? Output lags behind the input by tau. In your understanding, what does this mean? You can paste it on the chat box. It's not just important that you know that for a ramp input, amo ni siya. Kaya in principle, amo man gini siya class. Pero in terms of understanding what is happening to the process, what's your understanding of this? Si ano karon kung output lags the input by tau? Anong ginanamin niya sina? Kung sa Ilonggo, what's your understanding of it? You can paste it on the chat box, or you can use your microphone. Okay, glad that I have one in here. So what is written here? Gakaulihi, Doc. Correct, gakaulihi siya. Anong namin niya na? Let's say nagakaulihi siya by this much of time. Let's say your tau is, let's say 10 seconds. Anong implications na? Gakaulihi ang output by 10 seconds sa input. Anong implications na? Ang output means galag siya sa input with that specific amount of time. The amount of time na na-delay ang response. Okay, I'm trying to look for a very simple analogy to what I'm trying to say here. Correct na siya. Nagaka-delay ang output by this much time sa tau, meaning ang tau. The output is only measured only a constant time after the input is done. Before maghatag output, may input danay miss. Tama. Before ta may output, dapat may input. Kaya wala na siya, hindi gina mag-change ang aton output kung wala na disturbance sa input mo. So matabuan na ang input mo, daso ng output mo. Muna, maka-measure ka na sa corresponding response. Yeah. How will you, I'm trying to look for a very simple analogy to this particular principle. Ginapa-stable ya balik, Doc, sa ammonia na lag time. Ginapa-stable niya balik, Doc, sa ammonia nga lag time. I need a much simple explanation. Okay, 1 minute. Class, dalit lang kita. I will close the window. So, nag-stop na ang rain. Okay, example ha. My input after 1 hour. I'll just read this one chat. Nangin unsteady state na ang situation, Doc. Nangin unsteady state. Ma-unsteady, magin na siya, Marcel, once nag-change na ang imo input. Hindi na siya steady. Muna may controls kita. Difference ang output and input needs to reach steady state. Difference of the output and the input means to reach steady state. Could be. Pero generally, this is how it should be viewed, class. Thank you for your responses. Amuni. For example, ang imo thermometer may steady state value siya nga 25 kiara siya sa particular nga room. Dason, ginbutang mo siya sa isa ka bath nga ang temperature, let's say, 75 degrees Celsius. So, higher siya. So, gina-expecta nga ang aton nga, ang aton nga thermometer ma-register bago nga reading because kin-transfer mo siya sa sina nga bath. It would take for that particular thermometer to register the current temperature of the environment with the time value equal to tau. Let's say ang input mo 75 degrees Celsius, it would take for a thermometer with a time constant of 1 minute to reach that particular value. Your output will lag behind the input by this particular value. So if your thermometer has a time constant of 1 minute, 1 minute iya time constant, kag una-una ara siya sa 25 degrees Celsius nga environment, isaylo mo siya sa 75 degrees Celsius nga environment, mahulat kag isa ka minuto kag ang ina nga temperature ma-register siya 75 degrees Celsius. So nagalag siya kung ano man ang temperature nga ginasensya, kung ano na ang temperature sang bath nga gimbutangan mo sa iya, hindi na niya then i-sense, mahulat ka pa tau time for it to be able to sense the temperature of the environment where it is in. Do you get it? Naintindihan? Kaya kinalan, maintindihan nyo ang essence ng tau. It's the time for your system to register the temperature of the environment at that time you place it into it. So by the time, sang time na gibutang mo siya bisa environment, 75 degrees Celsius, gid ang temperature sa to, mahulat ka pa 1 minute for the tau which is equal to 1 minute for your thermometer to register also 75. Amo na siyang namin. Output lags behind the input by tau. So it will take this much time for your output to register the input temperature. So I hope you get it already. Okay? Now we go to the next if there aren't any concerns here. No more. So we go to the next. The next type of input is the rectangular pulse. This I have discussed under properties. Under properties of Laplace transform, and it's a function that is not so new anymore. The pulse is like this. Its magnitude is 1 over h on the duration 0 to h. And we have also derived this one, the corresponding Laplace transform. Now, ano naman ni siya ang rectangular pulse? So I'm speaking in the dialect so that you will understand. It's a sudden change in the input, but that change is not sustained. It's like you have your snack. It's like you have that particular disturbance only for a few seconds or a few minutes, and after that, it was returned to its original value. Like this one. The disturbance only occurred from 0 time to h time, and after that, it went back to its original value. Okay, in that case, your disturbance is said to be a rectangular pulse or a pulse type of disturbance. Now, your forcing function for this class, if you would represent it, your x of t, so I just use the x because it's our input. In the case of the pulse will be, you see this, 1 over h. I'll place here 1 over h. And then I multiply it. You see this? Actually, it's u of t minus 0. So I'll just place t, u of t minus u of t minus h. So this is the representation of your forcing function. That of a pulse of magnitude 1 over h for the duration of time h. We are clear with the representation? So as to its forcing function, I don't know, class not the forcing function. As to its Laplace transform, this is the Laplace transform. So I will change this one para clear lang. This is now your x of s based on the way we represent it in the thermometer. This is your x of t. This is your x of s. What is the response for this? So any question here? Magsulat per mi class clear gini dapat kay fundamental ni siya sa pulse. You write the magnitude here. the duration is multiplied to it in the form of unit step functions which has deviations on it. So if this is, for example, class, example lang ha, this one is like 1 to 2, your representation here for x of t would be 1 over h u of t minus 1 minus u of t minus 2. It really depends on what is the time duration in which this particular pulse of magnitude 1 over h occurred. So it's not always like this. Okay? It could be like this. So if it's like this, class, hindi na ni siya amo ang imo representations, ang imo nga iya inverse Laplace. You have to invert it the way it was inverted using during that time when I was discussing regarding inversion of Laplace transform. So this forcing function of magnitude 1 over h occurring from 0 to time h will have only the response written on the next page, which I'm going to show to you. If the forcing function that occurred is not occurring at 0 to h, but rather 1 to 2, the forcing function response will be different than the one that I'll be showing to you in the next page. Okay, let me clear that one out. Ini siya nga response para lang sa sini nga forcing function. If I change the magnitude, if I change the time duration, the response also changes. Okay? So the response also changes. So now, I will clear my drawings here. No, sige. If I will go to the next page, for the response to this type of, there's no response here. Okay, so there's no response here. I need to give you a sample. Why is no response here? I went straight to sinusoidal. Oh my, wait. Let me share a new board. I'll go back to the basics because it's not shown there. So you have 1 over tau s plus 1 over tau. This is your transfer function. Your forcing function for the pulse, let's say I'll change it so you will not get used to 0 to h. Let's say I'll change this also to a specific value. Let's say your pulse is a magnitude 10. And occurring from the time 1 minute to 2 minutes. Let's say my time units is in minutes. My time units is in minutes. So you have that. Is this clear to everybody? You can still follow. Juliana. Okay, you get x of s. I'd like to ask, can you tell me the x of s for this x of t? Let me check if you know how to do this. For the one who has a microphone, or for the one who can write on the chat box. What's your x of s for this? Okay, so maybe it will take time. So this is t e raised to negative s minus e raised to negative 2s. That's the Laplace transform of this one, class, this forcing function. Again, this is a pulse forcing function of magnitude 10 occurring from time 1 to time 2, whatever is the unit of your time. Now, what would you do? So to get y of t, you have this one. You have 10 e raised to minus s minus e raised to negative 2s. This is the x of s here that you will cross in here. The 1 over tau, I'll place the tau in here. Excuse me. And you have your s plus 1 over tau. Okay, you have that one. This one is a constant, so I'd better, okay, I'll keep it as it is. So I will simplify now my y of s. So it's 10 over s. And I will isolate these two terms, the e raised to minus s So you will see what we're trying to do here. Amo na siya class. So minus e raised to minus 2s. I distributed the s over 1, the s plus 1 over tau to the two terms in the numerator. Why do you think is that? Okay, somebody wrote in the chat box. Kulang pa over s, doc. Wait. This is S. Thank you for that. You have here S and you have here S. Oh, this should be tau. This should be tau. And you should have your S. And also you have your S. Thank you for that. I forgot the over S. So this is the Laplace transform of this forcing function. When you have written it in this form class, set aside this constant because anyhow your answers here will only be multiplied by this 10 over tau. What you're going to do next is invert. Just invert the expression. So you have the inverse Laplace of 1 over s times s plus 1 over tau. This is familiar, right? This is familiar. This is the same rational expression for the what? I would like only to invert. You see this one in the denominator. I'd like to invert only this for now. I will consider the thing that is written in the numerator later. Now, I did just that in the next page. I have this now. This is similar to what? This is similar to the rational expression that we inverted when we're talking about the unit step. Thank you for that, Joanna. Okay, and Joshua. It's the same as that of the unit step. So ano ganing answer sini sa unit step? What is our function of t here? This is 1 minus e raised to negative t over tau. However, what? This has a your unit step function is only 1 minus e raised to negative t over tau because your 1 over tau get multiplied with the tau. So this one has a tau, right? Our numerator this time does not have a 1 over tau. By the way, so if I will bring it here para hindi na ko magdala sini, sige, i-include ko siya sa babaw ha. Okay, erase ko. So, ang ako ni invert subong will be this. 1 over tau. Hala, time na. Okay. So, amo na ning response. Diin ko na siya aging ko ang 1 over tau. I took that 1 over tau in here. Para ang response naton do pariho lang sa step. Okay? You have here 1 minus e raised to negative t over tau. Now, ang problema lang class, this one. Your numerator here is e raised to minus s and in here it's e raised to minus 2s. Ano na siyang obrahon sina? So in your Laplace transform there in advanced math, this is the first step. The second step would be all the t's will be shifted by subtracting from them the value of the constant that appears in the argument of the exponential expression. Kung 1 di siya, amo man di siyang inyo i-subtract. There is a t. We're going to subtract 1 from the t there. If it's 2 on the second, that would be also the constant that you're going to subtract from the t in here. So what do you mean, Miss Ali? Your y of t then is equal to, okay, remember I placed this 1 over tau in here already in the numerator. So I will be left with the 10. So I place here the 10. For this first term, which has the e raised to minus s, this is what I'm going to do. I will have this 1 minus e raised to negative, so that t will be t minus 1. This would be over tau. This entire expression will be multiplied to u of t minus 1. That's our process. Okay, minus, I say minus. Is it a minus there? Let me check. Okay, minus, this one is separated by a minus. So minus, the same thing, it's multiplied to 10, but this time you will have 1 minus e raised to negative t minus 2. So you change all the t's in here by t minus that constant that appears in the exponential function argument. So tau. This thing will be multiplied to, dili ko na lang butang, u of t minus 2. You get it? Now, what you'll be getting now is this. Now, this is if you have here 10, and you have here u of t minus 1. In this part, you need to simplify, class. How would you simplify? You use the rules of exponent. What would be the rule of exponent in here? This should be e. Okay, my internet is unstable. E raised to, so this would be a product of two e's. This one is negative e raised to t over tau. So kung anong value, sinaklas, ibutang mo daw negative t over tau. Of course, this negative 1 over tau has a specific value. I suggest that you use the actual decimal value of that. So this would be e raised to a negative 1 over kung anong value ni tau times t. This one would be e raised to, this would be negative, negative. So this would be e raised to 1 over tau. U of t minus 1, because this u of t minus 1 is distributed to these two. This is for the first term. You will do the same for the next term. Okay? Since it's time already, we will continue this on Tuesday. We will have this finished. That way you will know how to handle pulse disturbances that are not as fundamental as the one that is presented in the slide. Nga wala siya gali na butangan response dayon. Okay? So I will continue this on Tuesday next week. But this is how you do it in this part. The next part will also have 10 times 1 or 1 times u of t minus 2. So that would be u of t minus 2. And this one also expanded. We'll assign a specific value for tau. That way we can simplify it. And you will have a specific response equation for a particular pulse function. You get it? Do you have any question for now? So we'll have lecture on Tuesday next week. So there's none? Sige ah. So we'll stop sharing now. So we will continue this next Tuesday. Class? Okay, bye-bye for now. We'll finish everything on this on Tuesday. Where you can also have, you can process also the problem set that I gave you to process. Thank you, everyone.
Thank you, Miss.
Okay,
Thank you,
bye.
Miss.
Thank you, Miss.
Bye-bye. Bye.